Okay, this month we are talking about a huge topic. We're gonna skip a rock over the surface and kind of dip into a little bit. We're gonna look at some code at the end. There's not going to be time to go into massive detail just due to the scope of these systems. But we're talking about migrating a project to CMake from Autotools. And if you're first, we'll talk about what Autotools is. So this is from Wikipedia. This is Unix family tree. Older dates are at the top, and newer dates, more recent dates are at the bottom. And Autotools is kind of created right around the middle of this chart, where you can see there's a bunch of these different flavors of Unixes. And this chart actually doesn't even show them all. It just shows the major ones that have survived. There's a bunch of other variants in here that I used one that was some weird combination of BSD and System 5. And depending on how you set up your include paths, it would see the system headers for one flavor or the other. So to deal with all these, all this change, in the 80s, vendors started making these workstations, these so-called 3M machines, 1 megabyte of RAM, a megapixel display, and a megaflop of CPU performance. And they all ran, not all, there's a couple like, um, one vendor had their own operating system called Domain OS Apollo. They had an operating system that wasn't Unix and it wasn't like anything else. But most of them ran Unix. Most of them licensed Unix because a lot of these workstation projects actually started from an academic environment as research projects, and then they became commercialized. Like the Sun workstation started at Stanford, became a commercial product. And when we get into the 1990s, particularly the early 1990s, the workstation market explodes, and suddenly there's all kinds of people providing these workstations, and they're all running Unix. But we don't have POSIX yet, so we don't have a standard for what system calls should look like. We don't have a standard for what the headers should look like for the C standard library. We don't have an ISO standard for C yet. You hit C90. But if you were talking like, the 80s before that, you didn't have that standard. We certainly didn't have a standard for C++. That wouldn't happen until 1998. So usually when you got a source distribution, whether it was commercial or open source, the first thing you had to do was spend some time editing build scripts and editing source files just to get the thing to compile. And if you were lucky, it shipped with some automated tests that would let you validate that your changes didn't break anything. Excuse me. So people started coping with the differences by writing shell scripts that would poke at your system and try to identify if the things this program needed were present on your system, or if there was multiple variants. Like before things were standardized, there was strcomp for comparing strings, there was memcomp for comparing memory, and there was bcomp for comparing bytes. And some systems had one, some systems had multiple, some systems had one of those three flavors. So you had to kind of poke around on the system to find out how you could compare strings. These days, just that's so standardized and well defined that you'd think it's kind of crazy that the vendors would provide environments with different ways of comparing strings, but they did. And these were manually written shell scripts. So as differences between systems came known, then you had to go manually update your shell script, and the person who discovered the difference had to let everybody else know that was using this kind of configure mechanism, that they all had to update their scripts. So around 1991, David McKenzie creates a tool called Autoconf, and this was just a simple tool that automated the creation of these configure scripts from basically a knowledge base of how you find the different things on a system. And it's important to understand that Autoconf is not run by the person who receives the software distribution to build it from source, but by the author of the software package to create a configure script that is included with the source distribution itself. So the end user of the source distribution gets the configure script, which is the result of running autoconf. And basically, you are describing the software requirements for your package to autoconf, and autoconf uses those requirements to generate a configure script that will do the right thing when you unpack the distribution. Now, configure scripts do things like locate system header files, they locate libraries, they determine maybe if a symbol is defined by a header, if a symbol is defined by a library, it determines things like extra command line arguments and build recipes for how to build shared libraries. And when the configure script runs, it takes the result of probing the system and generates some files from templates. One of these is typically a header file that holds the result of um, queries into the system in the form of a preprocessor symbols that are either defined or they're undefined. So they indicate the presence or absence of something. And then source code can include that header file and make a choice based on which preprocessor symbols are defined. And there's generally also a makefile that is generated so that the necessary command line arguments, directory locations, and so on can be substituted into build recipes for compiling the source code. And as more and more open source projects get created from a variety of authors, the Free Software Foundation, the people behind the GNU project, they create a coding standards guideline. And it's more than just a set of guidelines for your make files, although that's part of it. There's, a bunch of suggestions in there for how to write code to make it portable among systems. Some of that is rooted in all these differences between all these weird Unix flavors at the time. But some of it is also just general good advice for writing portable code. So some of it, even if you're not working on any GNU project, it's worth a skim over that document to read the section on portability. But it does recommend a structure for makefiles and a bunch of standard targets and naming conventions for variables and so on. And if you're going to write a makefile by hand, it's a whole bunch of extra stuff that you have to do. Writing, a target for installing your package, writing a target for building your package, writing a target for running any tests associated with your package, uh, writing a target for creating a source distribution of your package. So around 1996, a tool called Automake is created, and it helps simplify the generation of a conforming makefile. There's also a tool called Libtool. So Autotools generally refer to the three things: Autoconf for configuring the package, Automake for generating the makefile, and Libtool for creating shared libraries. And Libtool came about because some systems don't even have shared libraries. I think at this point every system has, every modern system has a shared library. But in the late 80s and early 90s, shared libraries were relatively new to Unix. Some systems had them, some systems didn't. And how you build a shared library has a different, kind of magic set of linker flags, or maybe it's not even the linker that you invoke. Maybe it's some special tool that you were invoking in ancient days to create a shared library that wasn't even the linker. Pretty much everything is standardized on using the linker to do this task now, but it still may have some specific command line arguments that are necessary in order to build a shared object as opposed to a static library. So those differences exist, and furthermore, there were differences in how you would access the code in such a shared library. Linux and POSIX has standardized on dlopen and dlsim, but other flavors of Unixes before that was a standard, de facto or otherwise, used different functions, and they had different mechanisms for accessing things. Certainly Windows doesn't use dlopen or dlsim. So in addition to saying how to build a shared library, Libtool has basically an API that provides a uniform interface for accessing shared libraries as a reusable component. Um, the basics of Autoconf is, again, you're going to describe your requirements in some file. This file is typically named configure.ac. None of the file names that we're going to discuss are mandatory. They can all be, customized with command line arguments or various options. So, but this is typically what you do. So you have a configure.ac file, and the configure.ac file invokes macros to perform. Um, let me see if I can say this right. You call a macro so that it expands into bash shell code that performs the check you're interested in and sets the result in a shell variable. And you can intermix raw shell code with these macro calls. And anything that's not a macro call in the configure.ac file just gets copied over to the output. So you can mix and match custom shell script code in the configure.ac with calls to autoconf macros that begin with AC underscore. And the macros basically just expand into a boilerplate recipe that performs whatever kind of check you're trying to do. So standardized checks for looking for a particular header file or looking for a symbol in a header file and so on. There's macros that do all those kinds of things. So you don't have to write that boilerplate over and over. They give you a macro that expands into the boilerplate. And there are a very large number of autoconf macros at this point for various tasks that you might want to, things you might want to check for in your configure script. There's also some helper tools called autoscan and autoheader that basically scan your source files and make educated guesses about what your configure script should contain and what your configuration header should contain based on the things you're using in your source code. Autoconf itself is a Perl script, and it is going to invoke the GNU M4 macro processor. If you never knew what M4 stands for, it's M with 4 letters, and the 4 letters are the remaining 4 letters in the word macro. So that's what M4 means. So Autoconf itself is a Perl script, so it requires Perl. Autoconf runs at GNU M4, and it has to be GNU M4. It can't be some other flavor of M4, so it requires GNU M4 macro processor. And the assumption is that this configure script is going to run under some kind of bash shell. And the other associated tools, Automake, Libtool, etc., those are also Perl scripts that end up invoking M4 to expand your input file as basically a bunch of M4 macros. So this is kind of a data flow graph. I just took this straight out of the Autoconf manual. You can take your source files and feed them into Autoscan. It'll create, what it guesses that you're going to need in your configure script called configure.scan. You take that and edit it and create a configure.ac. When you run Autoconf itself, it takes configure.ac and then aclocal.m4 and acsite.m4. These are just files that can contain additional M4 macros. So you might have custom macros you might have factored out some boilerplate across a bunch of your projects and created your own local M4 macros that do common tasks. You put those in the aclocal.m4. The acsite.m4, this is kind of a holdover from when systems were, a computer was a site and it was shared amongst a bunch of users, and they might have a bunch of M4 autoconf macros that are shared between different users of that computer. These days now, computers and people are one-to-one pretty much, so you're rarely going to see an acsite.m4 unless it's installed with Autoconf itself. You're not gonna, it's unlikely you're going to see a customized acsite.m4. And those feed into Autoconf itself, and you get a configure script out. And the configure script is what you include with your software distribution, and that's what the person who's going to build your package will run. Sorry, was a question? Okay. And AutoHeader, as mentioned, is similar to AutoScan. It scans your source code, and it scans your configure script input your configure.ac and generates a config.h template. The templates are typically named .in. And when configure runs, it will take those .in templates and substitute values into them and create the corresponding output file, in this case, a config.h. If you're using Automake, then it's pretty much the same, except that there is a makefile.am, am for Automake, and Automake processes that along with your configure autoconf script to generate a makefile template, makefile.in. So the makefile.am is the file that contains a bunch of calls to M4 macros that expand all the boilerplate for all the standard targets in a makefile that the GNU Coding Standards want to see. Here's the data flow of what happens when you actually run configure. It will do these probes into your system and cache the results of those probes in a file called config.cache. So the next time if you run configure again, it'll grab the results of config.cache so it doesn't have to run all the checks from scratch. And then you have your template files, your .in files that get processed to result in the output files, a config.h and a makefile, the makefile you feed to make to go and build the package after it's been configured. Now, that's just like a quick summary introduction. It still took us like 20 minutes just to talk about that. There's about, 800 or 900 pages of documentation that goes with the system. Do you really need to read all of it? No. It's a reference manual. So you can, like the Autoconf manual, read the parts in the beginning that explain how things work in general, and then you read the detailed section on the different macros that you might need to invoke to understand their arguments and what they do, what they check for, how they check for things. Similarly with Automake, the coding standards, you would skim over that to understand what kind of things is expected for a GNU package. Maybe you don't care about being a GNU package. You're just using Autoconf to solve some configuration issue for yourself. You wouldn't necessarily need to implement everything described in the GNU Coding Standards. There's a bunch of stuff in there about, formatting of code and style of code and things like that. You might get some ideas from that on how to, adjust your own personal style. You might get some good ideas. Maybe you think some of those ideas are, not for you because coding styles are very much subject to taste. Do you need to read the GNU M4 or the GNU Make manual? Probably not if you're doing, basic use of Autoconf. You're calling macros, you're not writing them. But if you end up writing macros or you end up in some sticky situation where the macro doesn't work like you expect, you need to understand how M4 expands these source files, and you need to understand, how M4 quoting works and how new lines get communicated between your configure.ac and the resulting shell script, and how comments get translated from the configure.ac into the shell script, and similarly how information gets communicated from your makefile.am with Automake into your actual makefile .in, and then from there via configure into the actual makefile that's going to be used to build your project. So if you get into an advanced scenario, you pretty much end up having to at least skim through these various things at one time or another. So that's a lot of stuff. This slide is purely my opinion. What I think the weaknesses of Autotools are. The biggest one is that it just assumes a Unix-like environment. So that means everything's done from the command line. Everything is built with Make. There's no support for IDEs. So you don't have any abstract project model that describes the targets and how they relate to things, which source files are being used as part of which targets. It's all implicitly encoded in the makefile itself. It's not explicitly described as any kind of project model. And as I say, advanced usage of this stuff requires you're pretty much going to end up bumping into understanding how M4 works. And really, the only thing I've ever seen in 30 years of computing, the only thing I've ever seen M4 used for is this Autotools stuff. And one place where I worked, they had to write a large amount of firmware and assembly language, and they decided to use the M4 macro language as basically a poor man's subroutine library. So they, instead of writing the same boilerplate code over and over again, they wanted to write it all in assembly for performance reasons, but they used M4 as a way to expand macros so that they weren't copying pasting the same piece of code over and over again. The other thing that is assumed knowledge of is GNU Make. Your makefile, if you just write the template yourself, you have to understand the weirdnesses of Make. It's very sensitive to white space. Tabs have to be used in specific places and not in other places. So it's a bit arcane. And Make itself doesn't have any mechanism for computing dependencies of source files. So if you include a header file into a source file, Make all alone doesn't know anything about that inclusion dependency, and if to run some other tool to analyze your source files and generate the dependency tree of source files versus header files, so that if you edit a header file, all the source files that include that header file will get recompiled. That's something that GNU Make doesn't do by itself. It's something that you have to manage. Autotools gives you a way of managing it so that you don't have to do that manually, but it's still an additional thing that you have to take care of with GNU Make. GNU Make doesn't have a built-in mechanism to take care of that on its own. There's also, because of the heritage of Autotools, a lot of the macros and even some of the portability advice given in the GNU Coding Standard, it's rooted in a time when all these Unix systems were so different. And where we are now is there's basically three platforms. There's Linux, Mac OS, and Windows. There's still some minor flavor variants, like there's BSD and there's Windows subsystem for Linux. But and really, you can even consider Mac OS at this point to be basically a Unix variant. It's not Linux, but POSIX as a standard has been applied to all these systems, so you don't have to worry about. And furthermore, the C and C++ languages have been standardized, so there's a bunch of things that you just don't need to worry about anymore. If you're on a POSIX compliant machine, you don't have to worry about whether unistd.h, you don't have to worry about whether that header file exists. It is guaranteed to exist on every POSIX compliant system, and the set of system calls that it defines are well defined by POSIX, and you can't call yourself POSIX compliant if you don't have that header file that declaring a certain set of functions. They can declare additional functions, but the POSIX baseline, you can't call yourself POSIX compliant if you don't have that. Similarly, the standard library in C++, for instance, the file system standard library just kind of eliminates a whole bunch of platform variations, like what is the function I call to find out if a file exists on the file system? How do I get to the parent directory of a file or another directory? How do I find out what my current directory is? How do I change my current directory? These are all things that the file system library in C++ 17 solves those problems for you. So you have portability layers that didn't exist back when Autotools was created. But the real big drawback of Autotools, in my opinion, is no support for IDEs, and there's no mechanism for obtaining dependencies from package managers like VC Package or Conan or what have you. It's not clear to me how Autotools is going to handle C++ modules from C++ 20. I don't know if they're planning on, makefile support for that through Automake or something. That would be the natural place to put it if they were to create some sort of support. I didn't find anything about that. Whereas CMake is moving forward with module support. Okay, but Autotools also has some strengths. It's not all bad. Chances are, no matter how weird your Unix environment is, a configure script generated by Autoconf is going to work. And many, if not all, of the GNU packages, and also many non-GNU packages, use Autoconf and Automake, etc. And by doing that, they're leveraging decades of expertise in Unix software configuration. Now, some of that expertise is legacy expertise that's only needed for these legacy environments. Some of the checks that you might be recommended to do in their coding standards are coming from this older time when there was a certain amount of variation. Whereas if all you care about is Linux, those checks are pointless because those things are always going to exist on Linux or Mac OS or even BSD. There's more. Those three Unixes have more in common than they have differences. And it is possible to get Autoconf packages to build on Windows. You still won't have IDE support if you're going to develop in those packages, but you can at least get them built using MinGW or Cygwin to provide the necessary environment to run all the ancillary utilities like sed and awk and bash and all that stuff, make, specifically GNU make, that you can get those packages to build. And a lot of these packages that rely on Autoconf that are made available through VC package, that's exactly what VC package is doing. If you pay attention to the package installation phase of VC package, when you consume one of these things, it goes down and gets MinGW and it gets a kind of a Cygwin environment or an MSys2 environment. It gets some kind of minimal Unix-like environment in which it can run the configure script, build all the code, and then create CMake imported targets for you to consume the package from CMake if you're using the CMake integration with VC package. So it kind of, wallpapers over all those cracks and presents to you a pre-built package that you just get to consume, and the CMake targets handle all the search paths for includes and libraries and so on. So CMake comes along and about 10 years after the whole configure thing was really a thing. I mean, Autoconf 1.0 gets released in 1991, but people were writing these manual configure scripts in the couple years before that. But CMake fundamentally has the attitude that they want something cross-platform. They don't want to assume that everything is Unix. And in particular, one of the goals of CMake is to create build scripts in such a way that they are consumable from your IDE, so that if you're a Windows developer and you're used to Visual Studio's IDE for manipulating your project, CMake generates such a project, and it's a natural fit. If you're a Mac OS developer and you're used to using Xcode projects, then CMake can generate an Xcode project. Another interesting thing falling out from this is that you can actually generate more efficient builds on Unix than Autoconf can generate. We'll talk about that a little bit later. So the big weaknesses there on Autotools get addressed by CMake, which is not surprising because it had about 10 years worth of experience coming later. For CMake, the input is a plain text file named CMakeLists.txt. The input language is custom to CMake with a simple syntax. You can add new functions and macros to the language. You can add those as just inline definitions, defining a function and then calling it, or you can use reusable modules. And CMake ships with a whole bunch of modules that extend the functionality in various different ways. And you run CMake on a CMakeLists.txt to create build scripts that are created using a generator. So there's a configuration phase where the system is probed to find out things that the build script will need, and then like the location of the C compiler or the C++ compiler, for instance. And then there's a generation phase where the build scripts are generated. And by separating the concerns of configuration and generation, you can add new generators to CMake without having to get intimately familiar with the configuration, the details of the configuration phase. And so there's a lot of different generators available for CMake, Xcode projects, Visual Studio projects, plain old make files. They can all be generated by CMake in the generation phase. And to configure things, just like Autoconf had a bunch of standard macros that did standard tasks for probing your system, CMake has a bunch of standard commands and associated modules. And modules are just a file where functions get defined in terms of other base level commands, functions and/or macros. And using standard commands and modules, you can do the same kinds of tasks: locate where header files live, locate where libraries live, determine if a symbol is defined by a header, determine if that could be a macro or it could be a declaration, a function declaration, it could be a variable declaration. Determine if a symbol is defined by a library. So not just whether or not the thing exists when you include a header, but whether or not you can get that symbol by linking against a particular library. Typically, the generator handles all the details of the platform build, so you rarely need to concern yourself with the specifics of the Visual Studio generator and whatnot. Pretty much they all have the same functionality parity. So you can exchange one generator for another, and you don't lose or gain functionality other than things like, obviously, if you're generating make files, you're not going to have that IDE view that you would have. You just get, but the idea of what the make files implement, that is the same across all. So you get standard targets for cleaning, all the built products for building the code, etc. So CMake doesn't assume the use of make files. So the way you describe your project is as a set of related targets. I mean, it can be unrelated if you just want to build a bag of executables, that don't share any code, or a bag of libraries that don't share anything. So they don't have to be linked to each other. You can build static libraries, dynamic libraries, executables, and custom targets. And the idea of a target is present in make files as well. With CMake, you're either building a library, you're building an executable, or you're building some kind of custom thing. The custom thing, we'll see how that comes into play. But most of the time, you're just saying, I need to build a library. Here's the source files in that library. And one library may require another, or an executable may require a library. So you have a dependency relationship between these targets, and there's commands that establish those dependency relationships. This isn't unique to CMake. If you dig into the way Autotools makefile conventions through Automake and the GNU Make Coding, or the GNU Coding Standards with the section on makefiles, they have an ad hoc way of relating things together through the use of make variables. The way CMake does it is the idea of a target is that it has requirements that are propagated to the consumer of that target. So if it's a library, one of the requirements for a consumer of that library might be, where do I go and find the header files for that target library? So I'm an executable. I depend on a library like, say, libtiff, the TIFF image library. Somewhere in the file system are the header files for libtiff. I need to know where those header files are located when I'm building my executable because I need to pound include them from the library, and where they are, I'm not particularly concerned with. It could be in any number of locations. I don't want to have to figure that out myself. I just want to say my executable needs libtiff, so when I attach myself to libtiff, when you build my source files, the necessary compiler arguments should be supplied to locate the header files for libtiff. Um, Again, this was just an introduction to CMake. There's an excellent book. It's an ebook. I think it costs $30. He's on his 20th edition. He's a contributor to CMake over time, so he's familiar not only with how to use it from the outside, he's familiar with how it works on the inside. The nice thing about his ebook is if you buy a license to his ebook, you get a perpetual license to all subsequent editions. I bought like a license to the 5th edition 4 or 5 years ago. Obviously, he's releasing new editions fairly frequently. I think he's releasing maybe 2-3 times a year. He's up to about 750 pages. It's not that length because CMake is that complicated to use, but it's because he's covering the whole suite of facilities of configuring your code, building it, um, running automated tests, and then running a packaging step or an install step. So if all you ever are concerned about is the configure and build part, you obviously won't need to read all 750 pages because you can skip the big chunk of documentation on packaging and you can skip the big section on installation and just worry about configuration and build. And even then, you won't need to read all of that because he has outlined the basic use case first, and then he goes into more advanced cases with examples as he goes through the various section of the codes or the various capabilities of the tool set. CMake.org has excellent online documentation. It's a reference. It's not a user guide. The professional CMake, I think, is more use case oriented. It is more of a user guide, and it's not a reference. He's relying on you to use the online documentation for reference. So he's explaining, here's the thing you're trying to do. Here's maybe 1 or 2 different ways you could do it. So I I like reading a user-oriented guide first to get my lay of the land, to get familiar with how things work for the typical kinds of things I'm going to do. I'll skip over the use cases I don't care about. Like if I'm not concerned about install, I just won't read that part. And I'll use the online reference to refresh myself. CMake does distribute, when you install CMake from the command line, you get a full local copy of all the help, so you can get access. So if you're working on an airplane on a 6-hour flight and you forget how to do something in CMake, you can get access to everything without having to connect to the internet. So CMake, like anything, has strengths and weaknesses. Again, this is just my opinion. I think sometimes the details of the platform-specific details of a generator are kind of hidden down in the implementation of the generator, and so sometimes it's a little bit difficult to figure out how to do something. And sometimes you have to write commands specifically to address platform differences, which it just means that the abstraction is a little bit leaky. Particularly, shared libraries still work differently between Windows and Linux. So sometimes you have to do a little bit of, if Linux, do this particular thing for my shared library. The CMake language itself is simple, but they have a backwards compatibility mechanism called policies. And sometimes the behavior of commands can change across version. You get a new version, and now suddenly your CMake it's not necessarily giving you errors, but it's warning you that things are going to change in the future. And so, keeping up with that can be a little tedious. You know, you install a new version of CMake, and your previously clean build now is issuing a whole bunch of warnings about things. Now you can manage that compatibility by with the policy mechanism, so that if you opt into the policy, you can shut up the warning about things are going to change. And it's good that it warns you that the behavior is going to change, but sometimes it just feels like I'm constantly chasing behavior changes as CMake evolves. But that's just the nature of evolving software. If you don't want to deal with that, just keep using the old version and don't update. Sometimes the variable caching mechanism rather in CMake can be a little bit confusing. Um, there's been more than once where I changed something and then I reran CMake and it used my cached result didn't and my change didn't propagate into the cache, so I didn't see the new behavior, and I was a little bit confused. So that can happen at times. But the big strength of CMake is basically nobody cares about Autoconf since 2007. CMake took over interest around that time, and you can see the interest in Autoconf. It's just an exponentially decaying curve. Really, the only people that are using it are the people that, they've been doing GNU projects for 20 years, and that's what they know, so they keep using it. And for whatever reason, they don't like Windows or they don't care about Windows, so they're not interested in the cross-platform portability that CMake gives you. They don't use IDEs. They use Emacs or VI, so they don't care about any of that benefit of having an IDE project that any of the either they're unfamiliar with the benefits or they just don't care. Um, it's I think Autoconf is pretty much in a legacy mode at this point. Whereas CMake just continues to gain traction over time. You can see that even that CMake interest curve hasn't flattened out yet. It has areas where it kind of is flat for a while, and then it peaks again. A big surge of interest comes in, and we're just continuing to grow over time. There are other build systems out there that either are trying to replace Autoconf or they're trying to replace CMake or both. And at this point, to displace CMake, you're going to have to be not just a little bit better, you're going to have to be like twice or 5 times better, right? The investing in a new thing is time consuming and involves, some switchover pain. And why do that if the gain is minimal? Other strengths, in my opinion, if you're going to build CMake from source, you only need a C++ compiler. So you don't need Perl, you don't need GNU M4, you don't need any of these other tools that may not even have been ported to your environment. But if you're going to build C++ code in that environment, you do have a C++ compiler, so you can use that to bootstrap CMake up from source. As you honestly, I've looked at the source code for CMake. I've never built it myself. I take that back. It was a problem something I was trying to understand about CMake, and I decided that the only way to do it was to build CMake myself, and so I did bootstrap it and build it once. But that was like once, a couple years ago, just because it was more to satisfy my own curiosity more than it was a necessity. I generally just install a pre-built package. When you install CMake, it has no other dependencies, no other external dependencies. It doesn't need some kind of particular shell. It doesn't need another command interpreter. It doesn't need any other kind of macro expansion facility or anything. It takes care of everything internally. And as I mentioned, it ships with a complete set of documentation that's installed locally. So you always have access to all the documentation. I find myself doing that a lot. I forget, the arguments to a particular command, and I just say CMake --help command, and I type in the command, and then the documentation for the command is coming out of my terminal. I like to do things from the terminal sometimes. I like my IDE, but I also like to do things from the terminal. I kind of like to use both for their strengths and weaknesses, for their strengths. I do believe that the local documentation is available in HTML form as well. Um, and I mentioned that you can even get a superior build experience with CMake even on Unix compared to Autoconf, and that's because of the pluggability of these generators in the back end. The Ninja build tool is often much more efficient at building a pile of code than GNU Make. And that's because Ninja was specifically designed for that purpose. It was specifically designed to be as fast as building a set of source code as possible. And so if you're on Unix and you have a CMake-based project, you can use the Ninja generator to take advantage of that. It also has, full IDE support because the generators can generate IDE projects. There's also a trend in IDEs these days to directly support CMake within the IDE, so you don't even, for instance, Visual Studio has CMake support, so you can use CMake directly in Visual Studio without using the Visual Studio generator, because Visual Studio has gotten improved CMake integration out of the box. There are other IDEs like CLion that also have the ability to use your CMake project as the project model inside CLion. But if you're using Xcode, I don't think Xcode has any such CMake support. Personally, even though Visual Studio has gotten this integrated CMake support, I personally find the Visual Studio solution to be preferable still. There's just a few minor advantages that I find for it. But they may iron out those differences over time, and the experience may end up being identical at some point. There's also a thing called the CMake File API. This is basically a way that you write a request as a JSON file. You invoke CMake, it reads the request from the JSON file, and it writes the response as another JSON file. And that gives access to the project model from CMake's internals without you having to write your own parser to parse CMake list input files and figure out the project model yourself or anything like that. So that file API is being used to provide integration into other IDEs and other tools as well. Package managers have gotten integrated CMake support, for instance, VC Package. It's really easy with VC Package and CMake to consume third-party libraries. Previously, where some of these libraries previously for Windows, just building them was a huge, huge endeavor. Like OpenSSH has like a bunch of crazy build steps, but they've automated all that through VC Package build recipes, and then it just plugs into CMake as a library that's ready for me to use. It plugs in as a target. Also, CMake has gotten support for C++ 20 modules, which require special build support. And that's, as I say, I don't know if that's available in Automake out of the box or Autoconf out of the box, if you may have to write your own special build logic in order to take advantage of that. Okay, so now that we've kind of laid the land on what these two systems are, there's obviously a bunch of things that are similar and some things that are different. They're more similar than they are different, so porting your Autotools-based project to CMake is doable. I was looking for an example project to convert from GitHub, and I kept finding projects where their configure.ac file was like 10,000 lines long. Obviously I'm not going to have time to convert all of that for a toy example, but I did find a small example, and we will look at that at the end. So, but basically this is a big refactoring, right? You're going to recreate your build, so you're not going to change. You don't want to change functionality. But you're going to recreate it in CMake to gain the benefits of like IDE integration or maybe easier consumption of third-party libraries through VC Package, what have you, whatever your motivation is. Or maybe your motivation is you've got one guy on your team that understands Autotools and he's about to retire, and none of the new people on your team understand Autotools, but they do understand CMake. So it's time to just bite the bullet and convert over to CMake because you're about to lose a bunch of institutional knowledge in that guy's head when he retires. This is a very real thing. So it's going to be the amount of effort is going to be proportional to the amount of build junk you've got in your Autoconf specific scripts and your Automake makefile and so on. Fortunately, the systems are not going to share files pretty much, except for source files. So you can have the two systems in your single source tree in your repository version control. You can have them both running in parallel until you're ready to switch over. And that means you can build up incrementally the CMake version of your build. Put it under continuous integration on a build farm. Make sure that all the if you've got different options for your system that can be configured by consumers of your package, you're going to want to make sure that you have a build job that configures those options differently so that you're testing all the choices. You don't want to just do the main line with the defaults and not test the options because you're going to have, consumers of your package that are using those options. So keep both systems working under continuous integration until you're ready to switch over. However, as I mentioned, there's a lot of legacy type stuff in an Autoconf system because it's from, it was initially created, 35 years ago, almost at this point. So consider modernizing your code and treating those legacy configuration options as something that you're not going to support moving forward. Do you still really care about environments that are so old that they don't meet the minimum standard of C90 or C++98? And if you do have to support those environments, just keep the Autoconf around, but recommend that people use, for modern environments, the CMake version, and then just stop updating the Autoconf. Eventually, people will migrate from these older systems and they can switch to CMake at that point. You're not going to go out onto the internet and delete all the old versions of your source distribution. So there's those older source distributions are always available as an option. Basically, your CMakeLists.txt is going to consume or subsume the same functionality that was in your configure.ac and in your makefile, because the configure phase of CMake will take care of the functionality described in your configure.autoconf file, and the build generator is going to handle 99% of the stuff that's in your makefile boilerplate. If you do have your own local M4 macros, chances are you'll be converting those into CMake modules that you share between projects. Presumably the reason you factored out the M4 macros in the first place, either because they were too noisy, you didn't want a 10,000 line file, so you factored out some macros, put them in the AC local.m4 file, so that your main configure file, your main configure.ac was short and easy to read. You can do the same thing with CMake modules. You can write your own CMake modules and put CMake function definitions in there or other code that you want to execute. You're gonna, if this is a big job, you're gonna need to manage a checklist of all the stuff that you have to do. And in any big refactoring, managing, that checklist of remaining work is important. And you can use any, method of tracking that. You can create tasks in Jira or, issues in GitHub, whatever way works the best for you. But one easy way to do this, and this is what I did in my little example library that I found. You can take the configure.ac and the makefile boilerplate, copy that into the CMake lists, and then just comment it all out. The hash character is the comment character in the CMakeLists.txt. You just, put a hash character in front of every line. Add your new content to the bottom and delete out the commented material as you replace it with whatever the CMake equivalent is. And once all that stuff's been deleted, then you know that you're basically done, and there's nothing left that you need to move over. Um, and as I mentioned, you're going to want to create a model of your project using commands in CMake. Your top level CMake lists has to have at least two things. It needs to say what's the minimum version of CMake that is compatible with all the CMake code that you've written. So that's a call to the function CMake minimum required. CMake functions, they typically have underscore separated words for their names. You may see in the documentation that sometimes they're written with uppercase names or mixed case names. For command names, CMake is case insensitive. Variable names, however, are case sensitive, so it's just something to be aware of. I like to write all the function calls in lowercase, just because I don't like screaming caps code. The project function is called once and gives the name of your project, the version of your project, what languages your project is going to use. And these are typically just pulled straight from the arguments to the Autoconf init, which takes also your program name and your version number. Autoconf init also takes like, an email address where bugs are to be reported. There's a field for a homepage URL and as an option to the project function. So some of these things have one-to-one correspondence, and some of these things they don't quite match. But it's not to say that you can't, communicate that bug reporting email address to your customers through CMake. It's just not necessarily an argument to the project function. And in the GNU Coding Standards, they recommend that each subdirectory contain its own little makefile snippet. Now, ironically, they mention recursive make as the way that those makefile snippets are all glued together. But recursive make is actually the slowest way to run make. But you don't necessarily have to do recursive make just because you've split your makefile logic into different makefiles. You can have your top level makefile just include all the subdirectory makefiles. The way you connect directories together in CMake is you use add subdirectory. And for each, I'm recommending that if you have subdirectories with makefile.ins or makefile.ams in those subdirectories, you put a CMakeLists.txt in there, each one of those directories, copy all the makefile template stuff into your CMake lists and comment it out. And initially, those files are just empty. So you just start with your top level CMake list is going to call CMake minimum required, and it's going to call project, and it does nothing else but call add subdirectory to get all the directories connected together. And even though there's no targets and there's no source files specified, this is a perfectly valid CMake project. It just doesn't happen to do anything. And you can generate an IDE project from this, and what you will get is a couple of boilerplate targets, for Visual Studio at least, that CMake always generates in order to manage the proper build dependencies, and nothing else. And you can build that, and it should build successfully. So you could check this in and get your CI system running, and just to validate that you're invoking CMake correctly to configure your project and then to do a build, and the build will just do nothing. So it's just a good way to get what they call a walking skeleton in place. And then you can just start going through your project incrementally and start moving requirements from the configure stage and start adding the necessary logic to get the build phase running. So a lot of Autoconf projects, they have that config.h header file that's generated, and because there's nothing in Autoconf that mandates this style. It's just the style that I've seen most commonly deployed. The config.h will have every single configuration result inside that one header file. And then every single source file will include that config.h to get access to the configuration results. Now, me personally, I don't like that because it's tight coupling of this one file. If you change any configuration setting, every single source file in the entire project has to be rebuilt. That's not to my liking. It's like a global dependency that if you touch that one thing, everything has to be rebuilt. On a very large system, this could mean, a huge build, even though you only change this one thing that's only used in the one place. But like I said, this is a very common style in Autoconf projects. Um, you can create in CMake what's called an interface library. And this is basically what CMake uses to model a header-only library. And you can create a header-only library for this config header. And you can use CMake to use the same config.h .in template that Autotools used, copy that over to another file that's used by CMake only. And the reason for this is that they're going to end up diverging as you migrate the configuration requirements over. And then CMake will configure that template into a config.h. That config.h will be attached to this target, that is this config library that you've created, this interface header-only library. And then all your other libraries and executables will be dependent on this config library. So what that looks like specifically is you call add library to create an interface library target, for instance, named config. You call configure file to take a template and process it into an output file, so config.h.in, you made a copy of that. That's going to be processed by configure file, and it creates a config.h. The config.h will be in your build directory, not in your source directory, because it's a generated file, right? It's a build product. The config.h.in, the template, that's a source file. That's in your source tree. You'll use target include directories for your config library to say that the config library's header files are located in the binary directory, the current binary directory. And when you are writing your own library targets and your executables, anything that needs access to this config.h, use target link libraries to associate your target with the config library. And over time, these details are going to start accumulating, especially if you have a lot of config checks going on. So my recommendation is just put all these in a config directory, localize all that stuff into one place. You may need to write a lot of, all your configure checks are going to kind of end up here. So you may want to isolate that all into one place, just the same way Autotools isolates it by putting it all in the configure.ac. Here it's going to be in a CMakeLists.txt, but if you have a lot of this probing of the system and so on, I just kind of recommend isolating it over here. And remember, as time goes on, you're not going to be able to share this config.h.in template between Automake and CMake because the syntax for substituting into it is going to be different, so you can't have them consume the same file. So if you're doing this in parallel, maintaining the two systems, you will have to remember that there's two places you're going to have to update. If you're making changes to config.h.in, you have to make the corresponding change to the CMake version of the file. Next, I recommend that you kind of work bottom up so that you start with the things that have the fewest dependencies on other stuff. So typically this will be libraries. And if you have simple executables, it might be an executable. But for library targets, you're going to call add library to create a library from source files. Don't forget to add the header files into the call to add library so that the header files also appear in the IDE view of the project. That's something that people often forget because they think of the stuff you put in add library is the stuff that gets compiled. But remember that the header files are an input to the compiler, and you want to be able to navigate to those from the IDE. So don't forget to add the header files. You need a name for the target. If your thing is called libfoo, just name the target foo. The only wrinkle is that the target names need to be globally unique. So if you have a libfoo library and you have a foo executable, then maybe you want to name the target libfoo instead of just foo, because you reserve the name foo for the executable instead of the library. If you have a lot of sources and you know that some of these sources are tricky in terms of they have configuration requirements, make a list of all the sources in the CMake lists and just comment out the complicated sources first and just work on the simplest sources that you know have the fewest dependencies. Start with the simplest thing and get more complicated as you go on. Always keep a working build, and as you commit things to version control, lean on your continuous integration system to run the build on multiple platforms with whatever configuration variation that you've got going on. To test all the combinations, so because you're going to run into a situation where it worked locally on your particular machine for your particular configuration choice, but then when you ran it on another machine or another platform or with another configuration, you forgot something. But you can lean on a bunch of stupid computers to run all these builds for you and report back which ones are failing. Now, there's the question of, you've got libraries. Are they static libraries or shared libraries? I think for a lot of people, static libraries are the most common because they're just using the library mechanism to separate out concerns. For instance, the Clang compiler, the whole thing is built from a big collection of static libraries. However, you may need to build shared libraries. CMake can build both. You specify a static keyword to add library if you want to explicitly mark the library as static. And similarly, there's a shared keyword to explicitly mark a library as shared. But a lot of packages let the user decide whether the library is built as shared or as static, in which case you omit the keyword and let CMake decide based on the setting of a variable, a CMake variable. The build shared libs variable will control that, what the default behavior is for add library when the keywords static or shared are missing. If you have just an executable, now might be a good time to take the source code for your executable, extract it into a library so that you can start writing unit tests against the library to be able to unit test the functionality in your executable instead of relying only on integration tests that invoke the entire executable. This is something that I do on projects that I'm changing, where the organization of the legacy makefile was just take all the object files and link them into one executable. Because I'm making changes on legacy code, I want to write unit tests for those changes to make sure that I'm not altering the behavior, that I'm fixing a bug or I'm adding a feature. I don't want to change stuff that I didn't intend to change. Okay, so the business of these configuration checks, and there's a whole bunch of check macros in Autoconf. We're not going to go over all of them. We'll just go over the few most common ones. A common thing is you're going to look for a header. AC check headers is the macro in Autoconf that looks for a header, and it implicitly creates a variable have whatever underscore h. So if you say AC check headers foo.h, you get have underscore foo underscore h is either defined or not. And that substitution takes place into your config.h. CMake includes modules check include file and check include file cxx. The only difference is whether they're running the C compiler to determine if the header can be found, or if they're running the C++ compiler to determine if the header can be found. Otherwise, the functionality is the same. And the result is stored in a variable that you supply, so you're not forced into a have whatever underscore h variable. You can be any variable name you want. And I think in Autoconf, there's optional arguments that let you specify the variable name. It just defaults to that. Most of the time, people just use that default. And then in your config library, in the CMake lists text where your config library is created, you'll call check include file to locate the header. You'll have the result in this have whatever variable or whatever variable you decided. You can decide if you have if this header is an optional thing or if it's a mandatory thing. If it's a mandatory thing, you can use message with a fatal error keyword to report a fatal error, indicating maybe your CMake script needs some assistance in locating where this header file is found. It looked in all the kind of standard places and it couldn't find it, so some intervention is required, or maybe it's missing it. That implies the user's missing a dependency on their system that they have to go and install manually, a manual prerequisite. And you call check include file before you call configure file, so that the result of the check, which is stored in a variable, is available to configure file when it generates the config header. In Autoconf, typically the config header template will have something like #undef have foo h, and then AC check headers for foo.h. If it's found, sees that little snippet, the undef, and switches it to a #define. In configure file, the mechanism is similar, except there's a different syntax. You write #CMake define have foo h, and when configure file runs, if have foo h is a variable that has a truthy value, and there's a couple different values that can evaluate to true in CMake: on, true, a non-empty string. Those all evaluate to true. It's kind of like Python in that regard. There's a truthiness, a set of values that evaluate to truth, and a set of values that evaluate to false, like off or false or empty string. And the #CMake defines get processed by configure file in the template, and then when the config.h is written out, you'll see, #define have foo h, or if the variable was falsy, then you'll see a comment commented out #undef have foo h. So it's a little bit different. This is the point where your config.h.in template is going to start diverging between the syntax that Autoconf expects and the syntax that configure file is expecting. And you're going to, as source files are migrated, that they're going to depend on these probes into the system looking for specific headers. You're going to be updating the config library, CMakeLists.txt, to search for the header, updating the template to use #CMake define. Configure file, before I just skip here to the next thing, configure file also has a way of doing defining the symbol always, and the value of the macro is either 0 or 1 based on the result of the truthiness of the variable. And just like in Autoconf templates, there's the variable syntax that you can use to just substitute the value of any variable as text into the template when it's expanded. So there's advanced uses of configure file, where you're filling in kind of boilerplate text into various places. It's very similar to Autoconf in that regard. So when you start migrating executables, similar to what we said for libraries, migrate the executables with the fewest dependencies first. Use add executable with a suitable target name and all the executable source files. Again, don't forget the header files. And use target link libraries to attach an executable target to its dependent libraries. And because of the way CMake works when it propagates requirements between targets, if you correctly set up the include search path for a library, you don't need to worry about configuring that for the target executable that consumes the library. CMake automatically propagates that kind of information between a library and its client. And it's not just the include search order that gets propagated. It's also things like you may have to define a specific macro when you compile source code that #includes a header file from that library. Some libraries, for instance, require that you define um, a macro that indicates the declarations in the when you're consuming a shared library, you might need to define a macro that indicates that the declarations in the header file for the client, header file for the library you're consuming need to be marked with a special export declaration. So when the library is consuming those header files, the declarations are marked as export, and that's when the library is being built, and then when you're consuming the library and you include that header file, you have to mark those declarations as import. It's kind of a Windows kind of thing, decl spec DLL import and decl spec DLL export. Um, there's a similar kind of mechanism for symbol visibility in Linux that where when you're building things, you may want to mark the symbols as private, and then when certain symbols need to be decorated as not, or as public rather, and there may be, undefineds that are controlling this behavior. At any rate, those requirements that a library specifies for clients, you can localize those requirements and compile flags, macros, include search paths. You can localize to the place where the library target is defined, and then clients of the library just pick it up automatically. They don't need to worry about setting all that stuff manually for each of the clients. Okay, so you've migrated some libraries. You maybe migrated one of your simplest library first, and maybe your simplest executable. It's just lather, rinse, repeat. Apply the shampoo algorithm. Keep doing that until everything's done. It's easier said than done, especially if you have many requirements. But that's why I was recommending you start with the simplest things, work one file at a time until you get an entire library ported, and then work on the next library, work on executables one file at a time. You're going to end up with configuration checks accumulating in your config library as you go. And when you're done, you may find out that your configure autoconf script had system checks that are outdated. They're no longer needed. For instance, checking for stdlib.h. It's just always there. You don't need to write a check for that. You may find out that your configuration requirements changed over time, and you used to require something that needed a configuration check, and then you changed the code. It didn't need the configuration check anymore, but nobody went back to the autoconf scripts and removed the corresponding check that was no longer needed. So you may just find some leftover stuff. See if you can, simplify that out, maybe remove that. Again, rely on your continuous integration, building and testing to make sure that just because you thought a configuration check wasn't needed anymore, that maybe it was only needed for a particular combination of user options. And by making sure that you're testing all the user options, you're going to make sure that you aren't you aren't deleting something that's actually needed, but only in an edge case. Now, once you get things working, you can start looking at some polish that you can put on things. As I mentioned, there's that ability in configure file to substitute variable text into the template. Configure file can be used to copy files from your source tree into your build tree. Maybe you need to copy some test inputs files into your build tree so that when you run your tests in the build tree, because maybe the test is going to create an output file as a result of running the test, and maybe it only accepts relative paths, or it expects the input file to be in the same directory where it's executing. So you can use configure file to just copy files into the build directory. I found that that's been handy, particularly with variable substitution. I use configure file to configure a test header that defines symbolic names for test input data, and I use copying of files with variable substitution to create an input file with the values of those symbolic test inputs substituted into the input file, so that when I run the test, I'm validating the contents of the input file symbolically and not textually. So I can change what the value of the variables are. I can change the actual text, but my source code that's running the test is referring to everything symbolically, so it's not connected directly to the text itself. So it's just a little bit of decoupling. I have found that just handy in some of the generated test data that I've been creating. And let's look at, okay, so we didn't talk about locating libraries. So sometimes you're going to depend on libraries you didn't write. They're coming from outside your project. Maybe they're assumed installed on the system. AC checklib and AC searchlib macros, searchlibs macros, locate libraries, and they're assumed that if they're found, that those libraries are appended to the link line. And the order in which you search for these libraries determines the order in which they appear on the link line when you're linking together an executable. So the order of those macros is important because you have to specify on a link command line, you have to specify libraries in such a way that if library A depends on library B, that library A is listed first. That will cause the linker to see the references to the symbols that are going to be supplied by B. The linker then consults the next library down the list, which if it's the B library, resolves those symbol references. If you reverse the order of the libraries, it looks at library B. The linker says nobody's using anything from this library, so there's the set of unresolved symbols is unchanged. And then it looks at library A, sees that A needs symbols from library B, but library B doesn't appear later in the command line, so those symbols remain unresolved. Sometimes people mistakenly write libraries with circular dependencies between each other, and then the library has to be listed multiple times on the link line. In my opinion, that's a design error. You should just fix that. You shouldn't need to list the library more than once. You should have a nice directed acyclic graph of your library dependencies so that every library can be listed once and resolve all the unresolved symbols. In CMake, what happens is when you use target link libraries, the order in which the libraries are listed has that same implied ordering. So if you have library A and library B, and A depends on B, then the best way to do it is to, declare that relationship by saying the target link libraries for A has a dependency on B, and then when you consume A from an executable, then that implicit relationship of A depending on B is brought along as another requirement of A that is brought to clients of A. I hope that makes sense because I'm kind of just talking about this abstractly in the verbal. But bottom line, you need to sometimes search for external libraries that you didn't build. And as I said, these libraries impose requirements on their clients. Preprocessor defines may need to be added to the command line before when compiling a source file in order to get the headers processed correctly. Additional include directories may need to be searched in order to find the include file for this library in the first place, and additional directories may need to be searched in order to locate this library for linking. In a traditional makefile type environment, you may need to juggle all these things yourself. CMake generally uses what's called a find module to locate things on your system. So you would use a find module to locate a particular library that is an external dependency installed on your system. If you use a package manager like VC Package, the way VC Package integrates with CMake is it will download the source code for this library that you depend on. It will build it in your build tree, and then it will set it up in such a way that when you use the find module to locate that library, it's locating the one that you built in your build tree as a dependency. So it works just the same as if you went and downloaded this library source code yourself, built it yourself, compiled it, put it in some kind of quasi-standard location on your system, and then set up the appropriate CMake search variables so that when you called the find module, it would locate the specific one that you built. So find modules by their own or find modules in combination with VC package, they work exactly the same way. There's a set of standard search paths that are used to locate things. And typically what the find module will do is if it does locate the library, it's create what's called an import target. And that's basically just a name, just like your target names that you created for your libraries and your executables. The import target is a name where all the client requirements for that library are attached to the name. So any special compiler flags that are needed, any special preprocessor defines that are needed, any special include library search paths that are needed, any special library search paths that are needed. Those are all associated with that imported target. So use the find module to find the library. It creates this imported target with all the associated client requirements. And then you use target link libraries to say, my executable depends on that library, and you name it by naming the import target that was created by the find module. So things are very modular in the CMake land. You don't need to specifically set up the include search path yourself, the library search path yourself, any particular macros that need to be defined for any source files that are compiled against headers for that library. You may need to check if a symbol exists in a library, or if a symbol exists, in a header, or if a symbol exists, if a name exists as a member of a structure. Autoconf has macros for these tasks. CMake similarly has functions and modules that perform the same task. In CMake land, it basically constructs a little piece of boilerplate code. It tries to compile it, and if the compile is successful, it considers the check successful. I mentioned, that when you use a find module, creates this imported target, so I pretty much covered what's on the slide already. This idea of targets communicate their requirements to clients makes your build logic cohesive, because all the requirements, when you create your own library target, all your requirements for your library are cohesive, recorded in one place, and that's the place where that library is built. Similarly, your consumers of those targets are decoupled from those details. So you've got decoupling and cohesion through the target mechanism in CMake. You may need to do some kind of arbitrary, just take this code and tell me if it builds. There is a function called try compile that you can use as a last resort to check that specific arbitrary code compiles successfully. Maybe you ran into a compiler bug with a specific, range of versions of GCC or something, and you need to identify that situation. If you can write a piece of code that if it compiles, then the bug is not present, that gives you a way to validate the behavior instead of coupling yourself to specific version numbers or a specific compiler even. You just, because really that's all what you care about is, does the behavior work? Not which version of GCC am I using and which versions had the bug, and I need to track all those different version numbers. Test the feature, the behavior directly, instead of getting caught up in a bunch of different version numbers or platform checks. Just take a piece of code, compile it. If it compiles, there's also a way to take code, compile it, and run it. And then if the running of the compiled code was successful, then the check was considered successful. When you do these try compile things, you may need to supply particular compiler flags or macro definitions and so on. There are CMake variables that can be used to control all of that behavior with try compile. In Autoconf, your configure.ac, it's a shell script with a bunch of macros that are going to be expanded in it to fill out the remainder of the configure script. That custom shell code can just be written as CMake commands that are executed at configure time to do the whatever custom stuff that you need to do. If you have a configure script that takes optional command line arguments to let the user configure some particular flavor, turn a feature on and off, do that kind of thing, CMake has options and cache variables. Options, it's just for Boolean values only. So don't think you can use option with a string value. You can't. If you supply a default string value, what's going to happen is going to be interpreted according to its truthiness. So if it's, you may end up setting the Boolean when you thought you were going to be setting a string value. The set function can be used to create cache variables. Both the option and the set function, when you're manipulating the cache, they have a description string. And the CMake, there's a curses-oriented GUI called CMake, and there's a graphical front-end program called CMake-GUI that help text that you're writing in the option or set function call, that'll be displayed to the user as an explanation for what the meaning of that variable is. So there's a user interface presented to let when the user's configuring the software that they can read that text and say, like, oh, I know what that does. I turn that off or turn this on, or this is the path to a file that that option wants you to set. Now, we mentioned the typical behavior is to generate like this config.h, and it'll have all these have fcontrol.h or have io.h preprocessor macros defined in it, and then the clients pound include that config.h, check the values of those things, and decide what's the appropriate header file to include in order to get something done. So one, a specific example to kind of walk through that is suppose you want to perform integer file descriptor IO using those functions open, create with no E, no trailing E, close, etc. And on Linux, you would include fcontrol.h. On Windows, you would include io.h. And on Windows, it would probably also yak at you that you're using, non-standard POSIX function names. So that's a detail you can iron out later by setting the appropriate compiler flags. And the Autoconf approach results in these two macros, either defined or undefined, that tell you the results of searching for these header files. And then that preprocessor logic has to be used whenever you include config.h in a client file. So you end up with that, if def have fcontrol.h, pound include fcontrol.h, end if pound if def have io.h, pound include io.h, pound end if. You end up with that little snippet repeated, and you have to pound include config.h before you have those if defs. End up with that logic repeated in every client file that wants to do file descriptor IO. So as I said, they have to include that config.h. They have to duplicate that preprocessor logic. So one way you can avoid that duplication, because duplication is always a source of errors, is you could create a little fdio.h, and have it include the config.h, and then have the preprocessor logic in one place to decide which header needs to be included in order to provide these functions. That's a little better. You still end up with this everybody that wants to do fdio.h is connected to config.h, and any configuration option that changes over time causes everybody to rebuild, even if the result of the search for fcontrol.h or the search for io.h, even if those results remain the same, these clients of the file descriptor IO feature, they're going to be rebuilt because they depend on that config.h. So can we do better than that? In CMake, we can invoke configure file differently. We can have one template that includes fcontrol.h and does not include config.h. Another template that includes io.h and does not include config.h. We invoke configure file with the right template to always produce this file descriptor io.h header. And now we just include that for any client that wants to do file descriptor io. They're not coupled to config.h, and now they're only depending on the specific feature, the results of identifying how to consume that feature, namely file descriptor io, instead of no other configuration changes will cause those clients to be rebuilt as long as it's only the file descriptor io that they depend on. I'm guessing that with suitable wizardry, Autoconf could be tricked into doing the same. I just don't see it in Autoconf related projects. I see a single config.h with a whole bunch of results of searching for various headers, and then I see the if-def stuff sprinkled throughout all the client files. It just seems to be the cultural norm over there. Finally, CMake is designed to support code generation at build time. Use custom targets and custom commands in order to get that done. I'm going to speed up a little bit so we can get to look at some code because we've been talking a long time. There's other stuff, other custom stuff that can appear in Automake, Autoconf projects. The shell scripts and the make files can be arbitrarily complex. Only you are going to know what those things are intended to do. So whoever's doing the migration is unfortunately going to have to understand both Autoconf and CMake. This is why I strongly recommend setting up the continuous integration as you proceed to make sure that, maybe some of that knowledge is lost and we don't know what these little snippets do anymore. So we're going to rely on continuous integration to validate our best guess. Furthermore, there's CMake has a testing facility where you use add test to add test cases at configure time, and that results in a little script being written out at configure time. That script will feed into ctest to run those tests. There's a way to use a Google test module to turn every single Google test case into a ctest test case. I don't see what I see in makefiles is typically just like a single target that runs that just runs the Google test executable. So if you want the equivalent, you can just use add test to run that command to run your unit test executable. There's also installation and packaging, which is also covered by the GNU Coding Standards in terms of the recommendations for the makefile. CMake similarly has facilities to support creating and install directory tree using the install command, and then you can create various packages using the cpack utility with different generators. And this is beyond what Autotools can do, because obviously Autotools doesn't know how to create a Windows installer MSI file. It knows how to make like tarballs of your source. But you can create a variety of packages, including Debian packages and Red Hat packages using cpack. Okay, so out on GitHub, I've got a fork of the old Usenet newsreader called TRN, where I've done some of this stuff. I've also got a fork of the old MS-DOS fractal renderer, where I've done also some of this stuff. TRN, I thought originally it was using Autoconf. It turns out it's using a different but similar system called metaconfig. The people that were metaconfig was created for Perl by Larry Wall, the author of Perl. When the Autoconf guys were getting started, they they liked some of the ideas of metaconfig, but they didn't like the specifics of metaconfig, and that's why they created Autoconf. So let's go look finally at some code here. Let me load up this. I found this project on GitHub called Mash, and Mash, github.com. It uses Cap and Proto, which we've talked about before. Yes, this is it. So, nope, that's not it. Or is it? I know what I should do. I should go over here, git remote-v. Yes, this is the one, Marble Mash. This is a genome and metagenome distance estimation using minhash. It is a Autoconf. Let's make this font a little bigger. It is an Autoconf project as a configure.ac. It's not too long. It's only 79 lines long, so reasonable. It has some options where the user can specify the location of cap and proto installed. It has dependency on cap and proto. It has dependency on the GNU scientific library. If it can't find the GNU scientific library, it will use the Boost library instead. And it has some source files. It is a makefile template that lists the source files. The source files get linked into a library, and then the executable gets built from the library and maybe this little wrapper. So it's not too complicated a project. So I pulled that down, and what I've got over here is, here's my top level CMake lists. Here's, as I mentioned, stuff that I didn't port over yet that I have left in as commented out. I haven't adjusted these compile flags for Mac. If the system name is Darwin, I haven't supported this little memcopy wrapper thing that he's got. I haven't supported installation yet. So all this install logic and uninstall logic, I haven't implemented that, but I implemented pretty much everything else. Now, because it depends on cap and proto, cap and proto does code generation at build time. It generates a C++ source file and a header file from your cap and proto definition file. Cap and proto is a evolution of protobuf. It's a binary messaging mechanism for communicating efficiently payloads across the network as well-structured messages. I've got a test directory that I've added. Here's the source code, and here's my little config directory. I started out with just this CMake minimum required and the project version and the languages I was using, and I set the C++ standard that this project uses. He had it hard-coded as an argument to GCC to select C++14. I'm specifying that as a CMake variable, and the CMake CXX standard required being on means all the targets that I'm going to build myself are going to require C++14. My little config library that I built, I made this config folder didn't exist in his project. I made it myself based on his configure autoconf checks, and I added some more because his code built on Linux. I'm building on Windows, so some of his assumptions about header files always existing weren't true, like sysIOcontrol.h and sysmman.h don't exist on Windows, neither does unistandard.h. He wasn't explicitly checking for that because his code was only being targeted towards Linux and Mac OS, but all of which have those files. And he's doing a little bit of file descriptor IO, so I have this search for io.h. So I'm checking for these include files to see if they exist. My template has This is going to generate a header file. So I'm using pragma once, include guards, and I'm using CMake define to create a header file. Let's bring this Solution Explorer over so you can kind of see what this looks like over here. CMake predefined targets and CTest dashboard targets, those are those folders contain boilerplate targets that CMake generates for its mechanisms to run CTest and to do the build dependency between targets. This little config library here, this is my interface only library. So if you look at the CMake list, it's an interface library. To have it available in the IDE, I have my template file existing, and I have the output header from the result of configuring that header file, so that I'm configuring into the build directory, not the source directory. So anything that is generated at build time goes into the build directory. This source group thing is just for IDEs, so I get a nice little folder over here that says my whatever.ins go into the CMake templates folder in the IDE view. It doesn't affect anything in terms of how things are built. It's just a nice way to organize files in the IDE. And if you have a makefile generator, it would just ignore this source group because it doesn't mean anything to makefiles. And I specify that my target include directories has an interface requirement. Sorry, my config interface library has an interface requirement to locate necessary include directories from the current binary directory, because that's the place where my generated header got put down when configure file ran. Configure file by default assumes the first argument is located in the current source directory or is a relative path to the current source directory, and the second argument is a relative path to the current binary directory. You can read, again, information about configure file. You can just read the documentation to see, the details of how that works. I'm using it in the simplest form here. I'm including this module, CMake module, check include file cxx. That's the thing that provides this function that I'm using here. My generated header is also part, I referenced it here as part of my add library. So I can navigate to that in the IDE, and we see the result was it found io.h, didn't find sys.io-control.h, didn't find sysmman.h, didn't find unistandard.h. Now, as I mentioned, in Autoconf, this have whatever thing, that's just kind of their convention. For me, it's just coming from the fact that I'm setting a variable to the result of that check, and the template, if you go back to the template had a CMake define that referenced this variable. The fact that it's called have underscore whatever underscore h is not important as far as CMake is concerned. It's just the name of a variable. And if whatever variable value exists when I call configure file is what is used to process. Oh, we got to go back to the template. Is used to process pound CMake define. Let's get that out of the way. So that's my config library. In my source tree, where all the source files for this executable live, again, I'm calling my library libmash over here in the IDE, because he's going to create an executable called mash. So I don't want to, all the target names have to be unique, so I can't call the library, I can't just call this, say, add library mash, and then down here say add executable mash. They're using the same target name, so they have to be different. Excuse me. So I just put, all his source files in this directory as the inputs to add library. Now, as I was building that up one source file at a time, starting with the simplest one. I found that it depended on the GNU scientific library. So I used the find package function to find GSL. If there's a specific find module that has specific logic for how to locate GSL, CMake will use that. Otherwise, it falls back to a standard algorithm that it uses to find whatever the GSL package is. The optional required argument says, like, you can go look for this. If you don't find it, it's a fatal configuration error. He also uses pthreads, and it turns out there's a standard abstraction around threads for the different platforms. So Windows threads, or I think you still have to kind of know which one you get, but Windows threads or pthreads, right? I mean, this is C++ 14. He could have just used std thread instead of pthread, right? He could have used a standard library. That would be better, because then let the standard library sort out how threads are provided by the operating system. But he's using pthreads directly. And you call this find package on threads, and if you go look at the documentation for the threads find module, it tells you when it comes back, if it found something, it will set this variable to tell you that the threads that it found was a pthreads kind of threads implementation. So in that case, it creates this imported target called threads, threads. The double colon is a scoping mechanism, just so you can have a way to scope imported targets. I'm just setting a variable to the name of the imported target that I'm going to depend on. So if I got pthreads, then go ahead and use this, because that's going to supply pthread style API. If I don't have threads on my system that looks like pthreads, well, let's go and look for a compatibility package on Windows called pthreads4w, pthreads for Windows. If I found that, and I'm putting required here because this find package threads required, find package threads will fail if the platform doesn't support any kind of threading. I need threading. I specifically need some threading API that looks like pthreads. So if this fails, it means there's no threading at all. If it succeeds and this variable is set, it means the threading that it found looks like pthreads. And this imported target will drag along all the necessary client requirements so that I can link against that with target link libraries, and I'm going to pick up my pthreads requirements that I need. Otherwise, I have threads, but it's not looking like pthreads. So I'm going to create or make another call to find package. I'm going to look for this pthreads for Windows. This likely means I'm on Windows, but instead of assuming I'm on Windows, I'm just going to say, let's go see if we can find this fallback thing that gives me a pthreads API on a platform that doesn't have, it has threading, but it doesn't have a pthreads API. So if that succeeds, I'm going to set my variable to the name of the imported target that pthreads4w found, so that down here, when I specify that my library depends on threading, it depends on whatever the value of this variable was, which was set to one of the two targets that I need. I'm saying I'm specifying here, down here, I am specifying the requirements for clients of the libmash library. So a client linking against libmash needs to look for libmash headers one directory up. What's one directory up? It turns out that that's where the mash directory lives. So they're going to include open bracket mash / command.h, right? So to find that, there's no mash directory in the current directory. It's one layer up. So my clients of libmash will have added to their include search path the parent directory of the current directory, so that the pound includes will work as expected. Furthermore, libmash depends on config, my config library. It depends on this mash cap and proto. We'll look at that in a second. It depends on these imported targets that were created when I went and looked for the GNU scientific library. And it depends on pthreads. Now, I mentioned that the order in which these link libraries are listed is important. I happen to know that this thing, depends on these. The config thing, it could have been first or last. It didn't really matter because config doesn't depend on anything else. GSL doesn't directly depend on pthreads. That's a requirement of my code. So there's some other orders of libraries here that would also work. I finally got my executable. It has one source file, and it depends on all the stuff in that libmash library. If we just look at the mash.cpp, it's just main, right? It's just including some files. He's not using his mash/whatever syntax here. He's using it, from the local directory. But he's just got an implementation of main that, does the stuff. So let's go look real quickly at this cap and proto business, because here we've got some generated code taking place. So first of all, I need to get cap and proto. I call find package on that to get cap and proto not only as library targets that I can link to down here, but also gives me this function. It's either a function or a macro. I haven't actually looked at to see. It's probably a macro. And it takes the name of two variables that will be populated with whatever generated source files were created by running the cap and proto tool. Whatever header files will be generated at build time, and the path to my cap and proto definition file. If you look at that, this is the thing. It declares some structures. It has some version stuff in here, and it's basically, this is a description of these messages that are going to be packed up and sent across the wire by the cap and proto library. When you run cap and proto, it takes those message definitions, it generates some code that does the packing and unpacking, and it generates a header file that declares definitions for those functions that do the packing and unpacking. So I'm creating a library. I put the protobuf, I keep saying protobuf, but it's actually cap and proto. Protobuf is an earlier version of the same concept. So down here, here's my cap and p file that contains my message definitions. Here's the source file that was generated. So this file, it's got a bunch of, Yak-like data tables and stuff like that. If we look at where this file actually is, I don't know if it's maybe hard for you to see because the font is small, but this is in my, if I browse files in the current directory, this is my build directory. So this file was generated in my build directory, not my source directory. And the generated header file, similarly, generated by cap and proto compiler, don't edit. This is off in my build directory, not in my source directory. It appears in the IDE project because I included them as sources. The value of those variables, I included them as sources for my mash cap and p library target that I created. I set up the include directories for this. This is where I needed I needed to go up a couple layers in the directory. And the reason for that is, if I go up, it's mash/cap and p/ minhash.capandp.h. That's how he referenced this generated file in his source files, because he was running cap and proto in his source directory, and the build outputs were getting mixed in with his source files. I didn't like that, so I'm using target include directories to keep the build products isolated from source files. And this mash cap and p library depends on these cap and proto targets that are brought in by cap and proto. Now, I didn't do any research to find out which of these are, actually optional. Um, it was just suggested that I use all these in the recipe when I ran the find package. So that's what I ended up using. And if we bring this over here, if I do a rebuild solution, I get some warnings, but everything builds, and there's still some portability issues because he's got assumption of memory mapped files using Unix memory map file utilities. He's got some file descriptor IO stuff using sysfcontrol.h. So that stuff is this code builds, but the porting isn't done, is what it amounts to. But we can see that it runs, compiling cap and proto schema min hash.cap and p. So I did rebuild everything. It reran the code generation step and recreated those generated sources, compiled them into a library that I linked against, and everything is satisfied in terms of compiling. Obviously, there's a couple of files that I modified because they had some Unix assumptions in there. There was also some code portability concerns. He was using dynamically sized arrays declared on the stack, which is a GCC language extension that's not standard C++. I've just replaced those with a std vector to get past the error because it's not going to compile on MSVC. And that's a little example of porting Autoconf and Automake stuff over to CMake. It's about the simplest example I could find. It got a little bit complicated, requiring GSL and cap and proto, which I solved by using VC package to get cap and proto, GSL, and the pthreads VC package. It basically does nothing on Linux, but on Windows it goes and creates that pthreads4w imported target, so I could resolve out the pthreads dependency. So I want to show you really quick my example that I did with the where I was talking about creating the fdio.h for file descriptor IO. I kind of cheated here. Like I have a if we look at my little configure script, which I have in my CMake directory, I am putting in, this CMake host system name so that I have one template with Linux in the name of the template and the other template with Windows in the name of the template, so I can just supply a variable name that expands to either Linux or Windows. It'll pick the right template. If we look at what those templates are, the Linux one, it just pounds includes fcontrol.h. The Windows one, go away. It just includes io.h. And any place I need to do file descriptor IO in my build directory, if we go over here, we need to go look at the other solution in order to see it in the IDE. So here I'm generating a bunch of stuff, but my fdio.h on Windows, because that's what I've configured it for, it just pound includes io.h. And any place where I need to do file descriptor IO, I include fdio.h. So I am including a header file that's providing me a feature. And I've left all the ifdef junk configuration crap. I've put that into CMake. And personally, that makes me happier because when I'm looking at source files, I don't like seeing preprocessor ifdef blocks. I like to just see straight includes of whatever it is that I need. This TRN. It's up on GitHub, and so is my other kind of similar case of iterated dynamics. Um, okay, that was a whole bunch of talking. I've even run over my normal lengthy time allocation, but if there are questions, we can take those. Yes, go ahead. Just feel free to unmute yourself. You know, ideally, what you would want to see is CMake to have Go language support. I mean, yeah, I mean, and CMake, I mean, CMake has support for CUDA, it has support for Fortran. I don't know what, right, but like you said, it's not trivial. Um, have you CMake? Um, they have a discourse server where that's linked from their website, so you can go on there and see if anybody's maybe come up with something. Another, I don't have a specific answer for you, but I would just say, look in the usual places, check with the Go community to see if they've created something themselves, or maybe another trick is to use GitHub code search to search for things that are doing something similar to what you've already done, and maybe you can find a more complete implementation. I would also I would go to CMake's code repository and open an issue to request Go language support. There may already be an open issue, in which case they'll point you to the open one and close yours as a duplicate. But I would do that because when you open an issue with them in their repository, other people can come in and vote it up, and that they can gauge the level of need in the community for such a feature. Yeah, if for instance, if there's I mean, it's kind of disgusting to, combine two build systems together, but if you have, some kind of native build system for Go that's already well developed in that community, you can always create a custom target and then just run the command to invoke the Go build. Yeah, you do. Yeah, I mean, it's, you know, yeah, it's a hack. Okay, anything else? Okay, then we will end it there because that was so much talking. I thank you for your patience sticking through the whole thing.